Hello, future engineers. Welcome to my YouTube channel. If you're still new to my channel and you like what I'm doing, please don't forget to share my videos to your friends and to your friends' friends, to your younger brothers and sisters who would want to take up engineering in the future, and to your relatives. That's one way you can keep me going, inspired, and refreshed. Now, if you find my videos interesting and important to your studies, also please don't forget to subscribe. Okay, let's have structural analysis problem 1.22. For the beam shown below, assume specific gravity of 7.86 for the steel beam. Determine the deflection at the free end of the cantilever beam. Modulus of elasticity 200 gigapascals. Express answer in millimeters. Approximate the moment of inertia of the wide flange. So this is the cantilever beam and it is W12 by PT3. These are the data of the W12 by PT3. This is in English system because 12 is the nominal depth of the wide flange, 12 inches, but the actual depth is 12.1 inches. The cross-sectional area is 15.6 square inches. Although the meaning of 12 by PT3 is 12 nominal depth, 12 inches by PT3, this is the uniform weight of the beam, 53 pounds per foot. However, or we will or I will present two solutions in computing for WB. One is, let's convert this to kilonewton per meter and compare it with the uniform weight of the beam based on its area and this specific gravity here. So it is a wide flange like W shape. So deflection WL to the fourth over 8 EI plus PL cube over 3 EI. By the way, this is for the uniform load over the cantilever beam, and this W here is the uniform load of 15 kilonewton per meter plus the uniform weight of this beam. It must be considered. Length is 4.5. P is 20 kilonewtons. And let's solve for I approximately by considering the section to be rectangles. So the width of the flange is for W12 by PT3 is 10 inches and 1 inch is 25.4 millimeters. So that's 254 mm. 10 times 25.4, so 254 mm. The thickness of the flange is 0.575 inch times 25.4, so that's 14.605 mm. The thickness of the web is 0.345 inch times 12 times 25.4, so that's 8.763 mm. The depth is 12.1 inches times 25.4, so it is 307.34 mm. So the depth of this web is 307.34 minus 2 times 14.605. So it is equal to 278.13. Therefore, the moment of inertia of this section with respect to the neutral axis is simply moment of inertia of big rectangle minus moment of inertia of these two hollow rectangles. And the width of that rectangle, hollow rectangle, would be 254 minus 8.763, and the depth is 278.13 mm. So I equals 1 over 12 times quantity 254 times 307.34 cube minus quantity 254 minus 8.763 by 278.13 cube. So moment of inertia of big rectangle minus moment of inertia of these two rectangles combined, that's the width, and that's the height or the depth. So I equals 174.8 times 10 to the 6 mm to the fourth. Therefore, EI is 200 gigapascals times this value, 200 gigapascals or 200,000 megapascals, 200,000 newtons per mm square times 174.8 times 10 to the 6 mm to the fourth. So the units would be newtons mm square. If you want to convert that to kilonewton meter square, we divide everything by 1000 cube. So dividing everything by 1000 cube, EI is 34960 kilonewton meter square. So that's our EI, and we express W in kilonewtons per meter, P in kilonewtons, so that the deflection at this free end there is in meter. Then multiply 1000 to make it mm. So let's compute the uniform weight of the beam. It is equal to 53 pounds per foot. Let's use this first. Times 1 foot times 3.281 feet is 1 meter. And 2.205 pounds, 1 kilogram, and 1 kilogram is 0.00981 kilonewtons, or 1 kilogram, 2.25 pounds, times 0.00981 kilonewton, 1 kilogram, or 9.81 newtons, 1 kilogram. Let's convert it directly to kilonewtons. So this is now in kilonewtons per meter. So it is equal to 0.774 kilonewtons per meter. Using the area, WB is 7.86 times 9.81 kilonewtons per cubic meter, specific weight of steel, times 15.6 area of this wide flange, 12 by 53, 15.6 square inches, times 0.0254 meter, or 25.4 mm. Let's convert that to meter directly. Per inch, quantity square. So this is now in kilonewton per meter. And it is 0.776 kilonewton per meter. So I'll use 0.776 because it is slightly greater than that, but I'm just presenting that either way supposedly will give us all practically the same value. So if you use 0.774, if you substitute, the answer will not be will not change. Will not change. The answer is the same if we round off values to 4 significant figures. Then substitute. The uniform W therefore is 15 plus 0.776. So delta is 15.776 times 4.5 to the fourth over 8 EI 34960 plus P 20 L cube over 3 EI. And delta E is equal to 0.04051 meter times 1000, so that's 40.51 mm. So that's it for this problem. I hope that you were able to follow and understand the explanations and the solutions.